Hello, everyone. So here's the hands-on portion for the collaborative filtering. So in this notebook, I'll show you how to perform a collaborative filtering type of recommender system. As usual, we will be importing the libraries and we will be using the movie lens dataset here. I've already pre-processed it beforehand. So we have to load the data first and then we just print it so you know what we're dealing with. As expected, it contains the movies and the genres for the DF genres, and then we also have the DF ratings for the ratings. So you have to map them, of course, have to merge them. So for user-based collaborative filtering, first thing that we'll be doing is to build the user item matrix. And then we will be retrieving the k most similar items. So we'll have to do some pre-processing, which is mean imputation, and then some similarity computation. And then we get the average rating of similar users. Then we recommend items. We also have another variation, which is getting the weighted average of similar users. And then we'll proceed to recommending the items. Okay, so let's show the code. So for this one, we will be using user ID equals 3. So this is our data set, and we see lots of null values. Okay, now let's retrieve k most similar users. Because we see lots of null values here, we have to do mean imputation. So I just fill it with the mean values here. And then we now proceed to similarity computation. In this example, we'll be using k is equal to 10, but again, you can replace this with whatever value that you could think of. So this means the 10 most similar users. And then we end up with the top users here. Now we get the average rating of the 10 most similar users. So now we get the ratings for all the movie IDs. And now we can recommend items to our user, which is user ID equals 3. Currently, there are lots of 5s. Now let's observe how other similar users rated those items. Right, let's check. So these are the ratings for those top 10 items. As we see lots of null values here, a very sparse data set. So another variation is we get the weighted average of similar users. So I've created this function here already for getting the weighted similarity. So we compute the predicted ratings based on that. And then we recommend the top items. Again, similar to what we have done earlier, let's observe how similar users rated those items. So mostly nulls. It's not really like a good data set for showing that. But that's really how it works algorithmically. Okay, let's proceed to item-based collaborative filtering. So in item-based collaborative filtering, we will build the item user matrix, and then we retrieve the most similar items. Again, as usual, we will be doing mean imputation. We will be doing similarity computation as well. And then finally, we get the weighted average of similar items. So for this example, we'll be focusing again on user ID equals to 3, but we will be computing the rating for item ID equals 1. You may just replace this with the other items that you want to be predicted later. So again, let's visualize the data set. So this is what we're going to be using. And then we retrieve k most similar items. And then we do mean imputation, similar to what we have done earlier. And then we compute the similarities. So these are the most similar items. Again, our ID here is 1. So that means these are the most similar um, items to ID equals 1. Now we get the weighted average of similar items. So this is how user ID equals you will rate movie ID equals 1. So let's check. So 3.5, 0.5, 0.5, 0.5, 4.0. And then lastly, we get the weighted similarity for the items. Because again, they are the most similar, right? Those five. So just get the weighted similarity, and I've provided the function here already. So that means the rating for that particular item is 1.7. So that's it for the item-based collaborative filtering. Let's proceed to latent factor models. So in machine learning, it's standard that we do train test split. So we will be doing that here. Let's use a train size of zero point 0.8. That means 80% of the data set. Now you can check the dimensions here. So 80K for the train and about 20K for the test set. And I've done some pre-processing here for you guys, which is inspect this in more detail. Um, so just to ensure that there are that the data is prepared for the SVD and NMF that we will be doing later, which is some prep work. I've also created this function here that checks the not null counts. Might be helpful for you guys. Just want to do some sanity checks here. So you can see that there are 80K not nulls for the train set, which is good, and about 19K not nulls for the test set. This test, forgot to replace this. It will be test. As you can see, the data set is very sparse. We only have this much non-null values, about 1.47%. Right, right. Very, very few. So let's do singular value decomposition. So we already have our train matrix, right? We will be imputing it because we need non-null values in our data set, so we have to do that. And the good thing is there is the singular value decomposition function already in NumPy. So with that, we could easily compute the SVD, and then we end up with the different matrices that we will be needing. So in this case, we will be using a factor of 100. So that means the top 100 factors that could approximate our original data set. Okay, so remember in singular value decomposition, you have the left singular matrix, the right singular matrix, and then the diagonal matrix here. So that's the S one here. Now that you have those, you will simply using the top 100. That's why you see that I have trimmed it. So just the top 100, top 100, top 100, and you just multiply them together. And now you end up with the same dimension as the original data set, even though you're using just the top 100. Now let's check the train set score. So I've done the necessary reprocessing here as well. So with the reconstructed matrix, and I've created a table here so we could easily visualize that. For example, for user ID equals 1, movie ID equals 1, the actual rating is 4, but the predicted is 4.21. But you can see there are lots of null values here. Of course, we do not include them in the evaluation. That's why we drop the nulls. You can only evaluate the ones with ratings. So for the ones that have ratings, you can see that our, okay, let's first check the null size after filtering. We end up with 80K. And that's a good number. So 80K. But yeah, the original size, as you can see here, is 500, 504. Wait, this is actually, no, this is 5 million items. So yeah, lots of null values as you can see. Yeah, it's 80K that we have right now. And if you evaluate, you will get these scores. So for RMSE, it's 0.47. And for the mean absolute error, it's 0.27. Now let's check the test set score, which is more important. So doing the same thing, we end up with this. So our RMSE is 0.98, practically 1. And then our means absolute error is 0.76. So how do you then interpret this? What is mean absolute error? I like MAE or mean absolute error because it's very interpretable. So in train set, that means your ratings on average are off by about 0.27 plus minus. So if my uh, predicted rating is a um, 3, for example, that means on average, the actual rating could be 3.27 to 2.73. So 2.73 to 3.27, that's range. So for test at score, you apply the same thing. If my predicted rating is 3, then the actual rating on average should be 2.24 to 3.76. That's what MAE means. Now let's proceed to non-negative matrix factorization. So it's pretty much similar. What we've done in SPV, the same applies here, but we're just making use of another algorithm. And in this data set, fortunately enough, we don't have negative values because the rating is from uh, 1 to 5, right? So we just, again, fill this with the mean is there are some null values. And we do the same thing. We make use of the non-negative factorization function, but in another library. So this is a scalar, not a NumPy. NumPy doesn't have NMF. So you just plug it here. We're also going to use 100. So you have your components here. So it's really just the W and H matrices that are important here. And then we will reconstruct them using the top 100 factors for components. And then let's evaluate it. Let's check the RMSE and MAE. So our RMSE for the train set is 0.53 and the MAE is 0.33. Again, the important one is the test set. So for our test set, the RMSE is 0.97 and MAE is 0.75. So the scores of NMF and SVD are quite similar for this particular data set. Let's check again. So 0.976 and 0.75 for NMF, but for SVD it's 0.76, 0.98. Yeah, very, very similar. So that's how you evaluate the latent factor models. And this is also how you would be implementing them. So that's it. These are the references.